This is the pre-lecture video for the first half of Chapter 6. The topic of this chapter is the electronic structure of atoms. Towards the second half of the chapter, we're going to be discussing electron configurations. Before we get there, we're going to talk about the wave nature of light, so we can get into the wave nature of electrons. Before getting into the topic of Chapter 6, let's come back to a couple of Chapter 5 problems. We'll also take a look at these problems in the first half or in the first part of lecture on Thursday. So this question is asking us to consider the enthalpy of combustion of a gaseous C7H16 molecule. So that would just look like this. I'm just drawing 7 carbons, 1, 2, 3, 4, 5, 6, 7. And I have hydrogens attached to these. Now this compound is going to combust to form CO2 and water. We balanced this reaction last time. We know this structure from Chapter 3. So we're reacting this with oxygen to form the 7 CO2 molecules and 8 waters. So we're making 7 double bonded CO2s and then 8 single bonded OH bonds. And so to balance this reaction, we needed 11 oxygens. Okay, so we can use the enthalpy of combustion chart to estimate this gas phase enthalpy of combustion reaction. Now the enthalpy chart from section 5.8, I'm looking at the chart from the lecture notes, it has like CH, CC, etc. on it. That chart can be used to estimate the delta H's of reaction by taking the sum of the bond strengths of the reactants, of the reactants, and then subtracting the bond strengths of the products. Now this just goes a little backwards from what you might expect the change to be usually products minus reactants, but this one is the bond strengths of the reactants because you're saying how much energy does it take to break all of these bonds. So we have 7, or excuse me, we actually only have 6 carbon-carbon single bonds, so it's 1, 2, 3, 4, 5, 6. So we have to break 6 carbon-carbon single bonds. We have to break all 16 of those CH bonds. And then we have to break the 11 O2 double bonds. I wouldn't get too concerned at this point about predicting structures. The goal here is just seeing if you have a reaction and you have the idea of what the bonds look like and the reactants and products, and you can choose the appropriate bond energy for the oxygen-oxygen double bond and for like the carbon-carbon single. So these bond strengths, this is 348 kJs per mole. We're multiplying by 6 moles of that bond. 16 moles of the CH bond, that's 413 kJs per mole. Now this works out to be an approximation, not a direct calculation, because these are approximate bond energies, not actual definitive bond energies. And so the OO double bond's 495 kJs per mole. So that's the energy if we add all this up. 6 times 348 plus 16 times 413 plus 11 times 495. That's the energy it would take to break all the bonds in the reactants. Then we get back the bond energies in the products. So in this combustion reaction, what it's going to do is ultimately produce more stable bonds. That's why so much energy is going to be given off. The carbon-oxygen double bond is 799 kJs per mole. We have 14 of those. 7 CO2s, 2 CO double bonds in each of them. And then the sum of the products, then we're going to have to add the 8 moles for water times the OH bond strength of 463. So it's like what we're exchanging are relatively weak carbon-carbon single bonds for relatively strong carbon-oxygen double bonds. And then the double bond O2 is being replaced with even more of these stronger CO double bonds. So we can either work this out, you can work it on your own if you wish, or wait for class. But we'll look at this problem, the opening part of class next time. We just have to do this arithmetic, work it out, and solve. We may not actually even work this out in class. We may just look at the problem, make sure that we see that the chart gives us only the delta H approximation for the substances being gases. It doesn't really work if we consider these substances being liquids or some other physical state. And then it only gives us, again, that approximation. It's not an exact calculation. It's just an approximation of the delta H of the reaction. And so it helps you maybe predict whether a reaction should be exothermic or endothermic. So then the last question we had from chapter 5 in the notes from last time was when a spark is given to a mixture of hydrogen and oxygen gas, water forms in a violent and explosive combustion reaction. Which statement is true? So the reaction definitely gives off energy. The reaction is not absorbing energy, it's giving it off to the surroundings. And then it's because the product's bonds are more stable than its reactants bonds. So then when you look at that reaction of 2H2 plus O2 goes to 2H2O, delta H is exothermic by quite a bit. So energy is given off by the reaction because the product's bonds are more stable, not because the reactants bonds are more stable. If the reactants bonds are more stable, it's going to take more energy to break the bonds than you get back by making the new bonds. This statement here, the reactants bonds being more stable than the products bonds, this would be true for an endothermic reaction, not for an exothermic reaction. So let's get into the topic of Chapter 6. Chapter 6 begins with the discussion of waves. And I think there's an important... the way this chapter walks through trying to talk about light and how it behaves like a wave, but it also has a bit of a particle behavior to it, helps then understand the electron, which is a particle, which ultimately also has a wave-like behavior. So photons, light, is really massless, and so you really have a particle behavior for something that's not a particle, and then the electron's kind of similar in that it's a particle, but then it also has a wave-like behavior. So let's start talking about waves first. So here we just see a standing wave. The number of waves that passes a given point per unit time is the frequency. It's like how many of these wavelength cycles do you complete per unit time? The wavelength is the distance traveled. So if you're looking here, this might be the distance that a light wave is traveling, and then this is just some amplitude relating to the intensity of the light source. And so the wavelength is how long it takes to complete a cycle of light. And so like radio waves have a very long wavelength versus like X-rays have a very short wavelength. So X-rays have a very short wavelength. We'll see a better slide on the next slide to take a look at that. And so here we see light of a wavelength that's shorter. Now if you have a shorter wavelength, then the frequency should be higher. You're going to be able to complete more of these cycles in a given unit of time because light's traveling at the same speed. So no matter what the wavelength of light is, it travels with the same velocity or the same speed. So the longer the wavelength, so the longer this is, then the fewer these cycles can complete per unit time. So then the lower the frequency. Then likewise, the lower the wavelength, then the greater the frequency. So the frequency, this is actually a symbol nu, not the letter V. So the speed of light is equal to the wavelength times the frequency. The way the units work here, wavelength usually is unit of something like length, meters, frequency, inverse seconds, and so then C would have the unit meters per second. And if you take a closer look at the frequency unit, sometimes you call this the cycles per second. So how many like wavelength cycles are you completing per second? And then this is usually understood or a unitless quantity, hence why the frequency is just inverse seconds. So let's solve a problem. What is the frequency of light with a wavelength of 725 nanometers? Okay, so the speed of light, c, this is generally a given on exams, but 3 times 10 to the 8 people usually remember. I usually use 2.9979 times 10 to the 8 meters per second. So if we're solving for the frequency would be equal to c over lambda. We're just using c is equal to lambda times nu. And so nu would be c divided by lambda. And so we'd have 2.997 times 10 to the 8 meters per second divided by 725 nanometers. We just want to convert this to meters to cancel out into the speed of light units. So 10 to the 9 nanometers per meter. Usually remember nano is 9, so there's a lot of nanometers in 1 meter. The equivalent would be we talked about this before in chapter 1, that 1 nanometer would be equal to 10 to the minus 9 meters. So we just have to make sure we understand these two different conversions and just use whichever one makes the most sense. So, in fact, I'm going to rewrite this with the second one because I think this makes more sense to me, that if I write this as 1 nanometer is equal to 10 to the minus 9 meters, then I can just enter this as 2.9979 e to the 8 divided by 725 e to the minus 9. So I can just enter into a calculator 2.997 e8 divided by 725 e to the minus 9 and very easily carry out that calculation. Now, at first glance, you may think that this is wrong because the frequency ends up being very high, but that's actually the correct answer. So if you do this calculation, I'm doing it right now, keep screwing it up, 2.9979 e to the 8 divide by 725 e to the minus 9 works out to be 4.13 times 10 to the 14 inverse seconds. Now this unit here is often called the hertz. So 1 inverse seconds also has the unit of hertz, so you can say that this would be 4.13 times 10 to the 14 hertz. Now we don't do a lot of conversions into like gigahertz and things like that, but you could convert this using the giga prefix, and that there's a kilo is 10 to the 3, a mega is 10 to the 6, a giga is 10 to the 9. It still doesn't really make it a very ordinary number. It's still a pretty big number. But you could convert that to gigahertz if you wish, or understand that you could, use a prefix in front of the hertz value to make this number not appear to be so large. That is, in fact, the correct frequency. So the speed of light's a constant. So if you think of wavelength times frequency as the wavelength is longer, the frequency has to become smaller. Fewer cycles can complete per second. And then so likewise the opposite, if you have a smaller, shorter wavelength, then the light has to have, therefore, a greater frequency in order for the same speed of light to be true for that particular wave of light. We can look at the electromagnetic spectrum and see that our colors of the rainbow kind of appear from like 400 to 750 nanometers, and that's the Roy G. Biv kind of backwards. So we get the red, orange, yellow. I guess yellow's over here. So red, orange, yellow, green, blue, indigo, violet. Okay, and so then we could also characterize and just remind ourselves that radio waves are generally the lower energy portion of our electromagnetic spectrum. They have, that wavelength of light's characterized as having a very long wavelength and hence a very low frequency. Very few cycles can complete per second. So very long wavelength, very low frequency. Then gamma rays have a very short wavelength, and then hence a very high number of cycles that are completing per second. Again, remember, all electromagnetic radiation travels in a vacuum at the same speed. So then, so Max Planck comes into this problem and is trying to understand why hot objects glow and have a color associated with them. And he started thinking, and I think this is the silliest picture in the world, but that instead of matter having an infinite energy landscape that the molecules can transition to, maybe there's individual discrete steps in energy that molecules can occupy. So maybe a molecule, if it's going to absorb energy, has to absorb some quanta of energy, some relatively high portion of energy. Now what this gives rise to is the idea that there will be states that should be stable, and then higher energy states that can be excited to if maybe the appropriate amount of energy is absorbed. And then really the hot object picture, like if you think of something glowing that's hot, why does it have a color associated with it? Or why does a flame have a color? Well, it's going to be because you have matter in all these different high energy states that are coalescing or decreasing in energy back down to some lower energy state. And as molecules are losing this energy in steps, it's giving that energy off in steps, and it's giving it off as discrete photons of light. And if those photons happen to fall in the visible part of the spectrum, then you pick up whatever color those wavelengths are corresponding to. So our visible light is only 400 to 750 nanometers. It's a very narrow range of the electromagnetic spectrum, but if we see light falling in that region, then we might see a characteristic color associated with those transitions. Now, Einstein won his Nobel Prize for studying what came to be known as the photoelectric effect. Now, the photoelectric effect, there actually used to be a much better image in the book that's been taken out. I'm not quite sure why, but the idea here is that metals can release electrons when you take light and you shine that light on the metal. Now, what the researchers did before Einstein came around was, and these included Hertz, and I think he actually passed away before this explanation could be discovered, or uncovered, maybe is a better word. But that what was found was you could take the light and increase the intensity, and it may not make the electrons flow off of the metal, but if you hit the right frequency, or the right wavelength of the light, then electrons could be released from the metal and observed and characterized. So then each metal had, or was found to have, a characteristic ionization energy, kind of the right amount of energy it takes to remove an electron from that particular metal. And so what was reasoned out by Einstein is that one photon of light of the appropriate energy is causing an ejection of one electron from the atom. So it's as if the photon is like a fastball, or it's like a particle that, as long as it has the right, and that's not really velocity because all the particles have the same velocity, but if the light has the right characteristic energy associated with it, or the right wavelength to carry that particular energy, then it could cause an electron to be ejected from a particular metal. And so then Einstein concluded that energy is proportional to frequency. So that there's this relationship between the frequency of light, nu, Planck's constant, h, and then the energy of the photon of light. And so since c is equal to lambda nu, and nu is equal to c over lambda, you can then rewrite the energy as being equal to h nu and also equal to hc over lambda. So the wavelength of light is directly proportional to the frequency of light. So if you increase the frequency, you increase the energy. And then likewise, if you decrease and go to a lower wavelength, then you would also go to a higher energy. So the idea here is the lower the wavelength, the more cycles that are completing, the higher the frequency is, the greater the energy of that electromagnetic radiation. And so this gave the sort of almost like, if you will, the wave-particle duality of light, that light was behaving like a particle because it carries an energy. And that energy can be used to do things if it's absorbed by the atom or by molecules. And so light, the photoelectric effect, can be observed in a lot of different phenomenon. Like you could break bonds, like we had our bond enthalpy chart that we were talking about earlier. So like an O2 bond can absorb ultraviolet light and break this bond. As long as light carries the right energy to break that 495 kJ per mole bond, and it's absorbed by the molecule, then it can serve to break that particular covalent bond. So the idea here is one photon of light can interact with one piece of matter, and in some cases cause one electron to be ejected from atoms if it's of the right amount of energy, because it's of the right frequency and the right wavelength. So let's look at a quick example of this photoelectric effect. So we're told sodium has an ionization energy of 496 kJs per mole. What energy of light in kJs per mole could ionize sodium? So if the light is characterized by its energy, so you can think of each photon as being equal to h nu, or hc over lambda, that whatever the photon energy is required to take one photon's energy, so we look at E is equal to h nu, or E is equal to hc over lambda, that these equations are giving us the energy of one single photon. That if you were to multiply this by, say, Avogadro's number, then that would give you the energy of the photons in units per mole. So if sodium has an ionization energy of 496 kJs per mole, then you would want to use a light source that carried 496 kJs per mole or greater. So you'd want the energy of your light to be greater than or equal to 496 kJs per mole, and then electrons should be ejected from from sodium. So then the question is, well, what wavelength of light corresponds to this energy? So again, we have this wavelength and energy, E is equal to hc over lambda. Let's remind ourselves that h is 6.626 times 10 to the minus 34, and that's joules times seconds are the units here. And so that's our Planck's constant. Let's work the energy that this light would have to carry for one photon. So let's go to one photon. So it's 496 kJs per mole of photons. So we just want to multiply 1 mole of photons, just like 1 mole of anything contains an Avogadro's number, 6.022 times 10 to the 23, and then Planck's constant is joules per second, so I'm just going to go to joules and say, okay, 1 kJ is 1,000 joules. Now this is going to be the energy of a single photon. Should be relatively small, and I think we'll see that it is. So 496 divide by Avogadro's number, and then multiply by 1,000. So that works out to be 8.24 times 10 to the minus 19 joules. Okay, so now if our light carries that amount of energy, then it would have the right amount of energy to break the electron free in sodium. So if we do a little rearranging of E is equal to hc over lambda, solve for lambda, lambda is equal to hc over E. So I should be able to plug in 6.626 times 10 to the minus 34 joules times seconds. Multiply that by the speed of light, 2.998. I don't know why I was using 2.997 earlier. It's 2.998 times 10 to the 8 meters per second. That if we then divide this by 8.24 times 10 to the minus 19 joules, let's look at what cancels. We cancel joules, we cancel seconds, we're left with meters. Okay, and so I'm going to write this number down over here. And so I'm going to do this arithmetic. So 6.626 times 10 to the minus 34 times 2.998 times 10 to the 8. And then divide that by 8.24 times 10 to the minus 19 gives me a 0.0000241. I'm just going to throw that into scientific mode. So I change the calculator mode over to scientific so I can get this correctly. It's 2.41 times 10 to the minus 7 meters. Now 1 meter is 10 to the 9 nanometers, so if I multiply that by 10 to the 9, that gives me the value in nanometers. So that works out to be 241 nanometers. Okay, so that is in the ultraviolet region. So our light, here's what I would know. 400 to 750, that's our visible. Lower in wavelength is higher in energy, that's ultraviolet. So ultraviolet is next in terms of energy. Then gamma ray and X-rays. And then IR would be next lowest after the visible, then microwaves, rewrite that, then radio frequency. So another mystery in the early 20th century was the emission spectra absorbed by energy emitted from atoms and molecules. So you can take neon or hydrogen or different sort of gases and pass a high voltage current through them, and these gases emit a characteristic color. So the question is, well, why is that? Why do these gases have these particular colors associated with them? Let's take a closer look. So one thing that we see is we get what we call a line spectrum. Now let's make sure we know what that means. So the sun or a light source, if you pass it through a slit just to get a narrow portion of the light and then pass that through a prism, then you get a rainbow developed for that light source. So this is common for white light sources like light bulbs and for things like the sun. Now, if you take the lamp of a hydrogen light source or something like a neon light source, then what you see is you get a discrete series of lines that emerge where light's observed following the same treatment. So take your H light source, like over here, pass it through a slit, and then look and see that you get this line spectrum. Or if you take the neon, like the purple color light, then it looks like the neon light in terms of having a few more different lines associated with it. So you get these line spectra. So the question is, well, why do we get these line spectra and how can we characterize them? So the hydrogen spectrum began to be investigated as early as the late 1800s. Balmer devised a simple formula that related to a couple of integers. So he just tried to find a formula where you could reproduce these particular wavelengths. Rydberg then came around and then developed a constant that you could relate the wavelengths at about 410 nanometers, 434, 486 I think is the one, and 656, that you could come up with those wavelengths using this equation relating one constant that's the same for all of them that came to be known as the Rydberg constant, and then constants like N1 and N2. And so then there wasn't much physical explanation. Niels Bohr came around and came up with a mathematical relationship and a better model for why this type of spectrum emerges and what it means. So Niels Bohr adopted Planck's assumption that energy would, that the atom of hydrogen, so we're most closely looking at just the H atom here in the H atom light source, that hydrogen can occupy perhaps distinct energy states. And then what we're seeing are that only certain orbits of certain radii are allowed. So we're really just looking at one electron spinning around a hydrogen nucleus. So you just have one electron free. So what the light source does, or what the high energy light source does, is it breaks the hydrogen-hydrogen bond so that we have a free H atom. Now it doesn't break every single H bond in the gas at the same time. It just breaks a few of them in a moment. Then the atoms are created in these high energy states that then coalesce or absorb back down into a lower energy state. So if we produce H atoms in these highly energetic states, then these states can react back down or transition back down to a lower energy state, and then a photon of light that would be equal to that difference in energy is then emitted from that light source. So the whole idea here, only orbits of certain radii corresponding to specific energies are permitted for an electron in an H atom. That's why we see only 4 distinct lines. The lowest energy state of any molecule or of any electron would be n equals 1. And so then energy is either emitted or observed as electrons are transitioned. So in order for the electron to go from n equals 1 to 2, then the atom has to absorb energy. And if an atom is already in n equals 2, then it can emit energy as it returns back to n equals 1. So n equals 1 is the lowest energy state. It's the lowest energy state on our diagram. 2 is higher. 3 is not quite as high. 4 is not quite as high. If you start thinking about the next highest, then you'd have 5, 6, 7. You have all these states coalescing all the way up to n equals infinity. N equals infinity is where you eventually have your free electron. Because what's going on is the n equals 1 to 2 to 3 to 4 are just increasing in their radius, and then just a little bit more each time. And you can actually create H atoms in like n equals 40 or n equals 50, where you get this like weakly bound electron to the H atom, and the H atom can be characterized as being in one of these supposed Rydberg states. It's in a very high n value. Now, so the atom has to absorb energy to go up. It emits energy when it comes back down. And when it emits energy, it often gives that energy off in the form of light. And so then you can think about, well, why do we not see, transitions? Why do we only see 4 transitions and not an infinite number? Well, it just happens to be that some of them are going to fall out of the range of visible light. So our H atom spectrum is really just looking from 400 to 750 nanometers to see those 4 particular wavelengths. So if we start thinking about some of these transitions, like if you think about the 4 to 3 transition, that's going to be too low. That's going to be in the infrared. That just won't be in the visible region of the spectrum. The 2 to 1 would be in the ultraviolet region of the spectrum, in the very high energy region, just like 3 to 1 or 4 to 1. Okay, now what Bohr gives us is a way to calculate these energies and then to calculate the wavelengths associated with these transitions, with the idea being that our n equals 1 to 2 to 3 is just a changing of the orbit size of that electron as it's spinning around the H atom nucleus. So electrons in the lowest state of a molecule, or in the ground state, or in an atom, the lowest state would be the ground state. Any energy state that's higher is called an excited state. And then since each orbit has a specific, since each orbit then transitions up or down, we can calculate the energy associated with those transitions by calculating delta E, and taking delta E as the final minus the initial, so the final state minus the initial state. And then each energy is equal to, like, you can write energy as a function of n, it's minus 2.18 times 10 to the minus 19 times 1 over the n value squared. So if you just do your final state minus your initial, do some arithmetic, then the delta works out to be minus 2.18 times 10 to the minus 18 joules, 1 divided by the final state squared, 1 divided by the initial state squared. So let's use this equation on the next slide. Or maybe on the slide after this to do a problem. So let's look at some of the transitions. So again, 2 to 1 involves emission of energy. 1 to 2 involves the absorption of energy. So a positive delta E means energy has to be absorbed by the atom for the electron to transition to that higher energy state. A photon is absorbed when the final state's higher than the initial state. So if we're going to go up to like 4 or infinity from n equals 1, energy has to be absorbed. If delta E is negative, that means energy is released, and then a photon can be emitted in that process. Now, photons can be absorbed to go up, but generally we're looking at high voltage energy causing the atoms to be created in these high energy states, and then light being given off when they return back to their lower energy states. So some of the key ideas here, to kind of summarize a little bit for the Bohr model: electrons exist only in certain discrete energy levels. So there is this quantized nature for the energy of the electrons in an atom. Energy is involved to transition as the electrons transition from one energy level to another. So energy has to be absorbed for the orbit size to increase, and then energy has to be emitted for the orbit size to decrease. And then n equals 1 would be the lowest possible state, and then there is no n equals 0, or there's no electron falling into the nucleus. In fact, Bohr has just to assume that the atom is stable. It doesn't really have any part of the equation that shows why the electron doesn't ultimately just collapse into the nucleus, other than it just begins with n equals 1 as being the lowest possible value of n. But it also then makes sense that atoms really do exist and the electrons don't just collapse into the nucleus, so that's a pretty good assumption. And then one of the downsides of the Bohr model is it really only works for hydrogen. And it can be technically applied to other ions. And one of the ways that that can be done is the energy of N for one electron ions could be said to be equal to minus 2.18 times 10 to the minus 18 joules, and then times Z divided by N, where Z is a nuclear charge. So, for example, if you had like helium plus, helium has one electron, or excuse me, helium has 2 electrons, but helium plus only has 1 electron. So a 1 electron ion, we can plug in the Z is just a nuclear charge, helium Z would be 2. So if we're doing this for helium plus, this would look like minus 2.18 times 10 to the minus 18 joules times 2 divided by N. Okay, now we can do this for like lithium 2 plus or beryllium 3 plus, but you know that's really not all that great because those ions aren't really common. So we're going to have to come up with some other way to describe larger atoms. We're going to see that that's orbitals and that's electron configurations. We'll talk about those during the second half of Chapter 6. So let's look at a couple Bohr examples. So if an electron in the H atom transitions from n equals 2 to 1, would light be absorbed or emitted by the atom? So 2, in terms of energy, is higher than 1. So energy is going to be released by the atom. So light would be emitted by the atom as the electron undergoes this transition. Okay, so light's emitted. Then can we calculate the wavelength of light associated with this transition? Okay, there's no equations I don't think we're going to give you for this particular topic. The two I would remember are either the energy as a function of n is minus 2.18 times 10 to the minus 18 joules times 1 divided by n squared, or the final minus the initial equation. You can memorize this, or you can just use the previous equation to help you solve for it. It's minus 2.18 times 10 to the minus 18 joules times 1 over the nf squared, and then minus 1 over the initial n squared. Okay, so our final n is 1, our initial n is 2. So we can throw that into a calculator. So that gives us the energy change. Now this is the energy change for the atom. So the atom is like our system, and the wavelength of light that can be created, that's like our surroundings. That would be the energy being lost by the system given to its surroundings in the form of a photon of light. So we just go minus 2.18. So just like I've talked a fair bit in Chapter 5, just enter the minus signs as you see them, and don't try to get too fancy. Just do minus 2.18 times 10 to the minus 19, parentheses, 1 divided by 1 squared is 1, minus 1 divided by 2 squared, which is 1 divided by 4. And so that works out to be minus 1.635 times 10 to the minus 18. Energy lost by the atom is gained by the photon. So our photon energy should be positive, should always be positive. It's plus 1.635 times 10 to the minus 18 joules. So energy is lost by the atom, the energy is negative, gained by the photon. So the energy of the photon is the negative of that of the atom. And so then we can plug that energy into the E is equal to hc over lambda, or lambda is equal to hc divided by E. And so I'm not going to write out h, I'm just going to use it and say it out loud. 6.626 times 10 to the minus 34 joules times seconds times 2.998 times 2.998 times 10 to the 8, and divide that by the energy of the photon of 1.635, which is only good to the third sig fig. In fact, this number here, you could actually look it up more precisely than just 3 sig figs, but that's probably good enough for most of the examples we will do in this class. And so that gives us 1 to 1, so it comes out in meters, so I get 1.21 times 10 to the minus 7 meters. Convert that to nanometers, it's 121. So if I multiply this by 1 times 10 to the 9 to go to nanometers, that gives me 121.5 nanometers. So call it 121 nanometers. Okay, so that's a photon of light that would be emitted for the hydrogen atom transition from n equals 2 to 1. So if you took a ground state H atom and shine a 121 nanometer light on the atom, and then tune it very precisely to that transition, then it will absorb that photon of light to transition the electron from n equals 1 to 2. So now, would an electron transition from n equals 3 to 1 have a greater or lesser wavelength than 2 to 1? So if we compare 2 to 1 to 3 to 1, where 3 is higher in energy, the difference of energy here is greater. The greater difference of energy should lead to an even lower wavelength, because the lower wavelength corresponds to a greater energy. So if we want this energy to be higher, we got this inverse relationship, we want that wavelength to be smaller. So the wavelength should be smaller. So the wavelength for the 3 to 1 transition will be less than the wavelength for the 2 to 1 transition. So then just a couple more slides and equations for today. So de Broglie theorized that that light can have material properties, then material should have wave properties. And specifically, material or matter that has a really low velocity, or a really, really small mass. So the wave nature of matter should be more on the size of that matter as the mass of the particle grows smaller. And so that kind of is getting towards the electron being relatively small, relatively light. So that should be the particle of matter that's going to be most likely to have a wave-like behavior associated with it. So his equation, which he empirically derived, is that h divided by mass velocity is the relationship to calculating what is sometimes symbolized lambda d for the de Broglie wavelength. So we take Planck's constant divided by the mass of the particle times the velocity of the particle. So this v here is velocity. So it's the velocity of a particle with the mass of m. And we'll solve some problems with this later in class, perhaps. So it's a really easy to use equation. You get a number, but the idea here is that that for electrons, that their wavelength, their natural wavelength, is on the order of the path of an electron around an atom. So the electron is going to be best described as behaving as a wave as it's spinning around a particular nuclei. So the uncertainty principle, Heisenberg showed that the more precisely the momentum of a particle is known, then the less precisely its position can be known. And so there's this fundamental limitation that the uncertainty in position, delta x here, this is a weird unit. That's the uncertainty in the position of a particle, is what delta x means. Delta here is almost like an error term. It's like the uncertainty in x. So imagine you have an electron on its way to a positive potential. And so then there's some distance term here. And so then the electron has some mass and then some uncertainty for where, or it has some position, not mass, has some position, x, where x is some measure of length, perhaps measured in like a meter scale. And so the x here is the position, and then the plus minus is the error, the uncertainty in that position. So like if your electron here has a particular position, let's say it's 1.5 times 10 to the 5 meters, the question is well, what's the uncertainty in the position of that electron? So let's say it's 1.5 plus or minus 0.2 quantity times 10 to the 5 meters. The uncertainty would be 0.2. Delta x would be equal, in this example, to 0.2 times 10 to the 5. So it's not the position or where the electron is, it's how well you know that position to be characterized has a limitation on how well you can understand the momentum of the particle. So delta mv would be the uncertainty in the momentum of the particle. So this is the uncertainty in the particle's momentum. And then the mass is usually fairly constant, so you might actually write this as m delta v. So this is really the uncertainty in the velocity of the particle. So the uncertainty in the particle velocity. So like de Broglie found that the electron can have a wave-like behavior, Heisenberg finds that it's a wave that you don't quite know where it is in any given moment. So you have a large uncertainty in where you think the particle is given what you believe its velocity to be. So you just have this limitation that you can't precisely know where an electron is and what its actual velocity it is at that current moment. So you can't exactly know where an electron is and what its velocity is at that exact moment in time. What this is going to lead towards, or the conclusion of these two ideas, the uncertainty principle and the de Broglie wavelength, is it's better to think of electrons in terms of a probability of where you expect to find the electron, which is the idea and the notion of orbitals. So for larger atoms other than H, it becomes almost a requirement that we discuss the probability nature of where electrons are around those atoms, that becomes the idea of electron configurations and orbitals. So the second half of chapter 6, other than a little bit of theory to get us going, really ends up in somewhere we've probably seen before, coming up with things that, like for carbon, that the configuration of carbon, you might remember, is a 1s2, 2s2, 2p2. Now maybe you didn't quite know what the 1s and the 2s and the 2p meant, or why it was that those were orbitals and descriptors that we were using, but we will try to describe where they came from, what they mean, and how we put those together for larger atoms as we wrap up chapter 6 next Tuesday. Okay, that's all for today's pre-lecture video. Hopefully this gets you a start on chapter 6. See you in class on Thursday, and take care.